Welcome to the deep dive. We're jumping headfirst into some really interesting material today.
Yeah, feels like a good one.
We're pulling insights straight from lecture excerpts you shared. And our mission, well, it's to unpack these core ideas about managing water, specifically runoff.
And how we measure it traditionally.
Exactly. We'll dig into the downsides of just diverting water away and look at the main ways engineers calculate, that peak runoff, pulling out the key stuff for you. I'm actually pretty excited because understanding the why behind the old methods gives such great context for newer stuff like low-impact development.
Absolutely. Think of this as the foundation. These traditional ideas, they're really crucial for getting why LID is even a thing and what it's trying to do differently.
Okay, let's get into it then. The main idea, especially with LID, low-impact development, it's really about changing the hydrological cycle, right?
Fundamentally, yeah.
Yeah.
How water moves through the environment, rain, soaking in, running off.
Got it.
And the sources really stress this point. LID is focused on the runoff itself, the water flowing over the surface.
Okay, runoff.
Which is different from traditional drainage.
Yeah.
That usually means the pipes, the ditches.
Yeah.
The infrastructure built to just get rid of the water.
Right, the gray infrastructure, the big concrete stuff.
Exactly.
And that takes us right to the problems the sources highlight with that whole approach, just diverting the runoff.
Yeah, there are some big ones. First off, cost.
Always a factor.
For sure. You're designing, building, and then maintaining these massive systems, pipes, culverts, treatment plants. The life cycle costs, they're huge.
And the sources link that to sustainability, the economic part?
Directly, yeah. Just moving water isn't free. There are real long-term costs involved.
Okay, cost is one. What else?
Well, the environmental side.
Pollutants.
Pollutants.
The water picks stuff up.
Everything. Oil off roads, chemicals from lawns, general gunk, and the diversion system collects it all.
And sends it downstream.
Yep. And here's the kicker. You take pollutants from a wide area, maybe at low concentrations, and you funnel them into one concentrated flow.
Okay. So it's like a pollution superhighway.
Kind of.
Yeah.
And nature's filters, plants, soil, they can handle dispersed stuff okay. But the sources say they just get overloaded when you dump this concentrated slug on them.
Right. Too much all at once. Makes sense.
It's like trying to clean an oil spill with a coffee filter.
Good analogy. And there was a third downside mentioned. Something about groundwater.
Yeah, groundwater table depletion. This one's maybe less obvious.
How does that work?
Well, if you design everything to whisk water away super fast...
Which is the traditional goal, right?
Yeah.
Get it away.
Exactly. You're actively stopping that water from soaking into the ground right where it falls, especially under pavement, buildings.
So no local recharge.
Precisely. The water's gone, maybe treated miles away, maybe just dumped in a river. So the soil under the development doesn't get that water, affecting soil moisture, potentially lowering the local water table over time.
So massive costs, concentrated pollution, and you might actually be drying out the ground locally.
That's the picture the sources paint of the traditional approach's downsides.
Okay. But, rain happens, water flows, whether it's a forest or a parking lot.
Right. And when you get a really intense long rain, that maximum flow rate you see across the surface,
Yeah.
that's what engineers call peak runoff.
Peak runoff. Okay.
It happens everywhere, naturally. But it tends to happen much faster and maybe in larger amounts on engineered surfaces like asphalt or roofs.
And why do engineers need that number, peak runoff?
It's super practical. The sources say it's used for sizing infrastructure. Think culverts under roads or the storm drains in a city.
So you need to know the maximum flow to make the pipe big enough.
Exactly. You design for that peak, that worst-case flow, so things don't back up and flood. It's critical for designing all that traditional drainage infrastructure.
Got it. Okay, so how do they calculate it? The sources mentioned two main ways.
Yeah, two common methods. Let's start with the rational method.
Rational method. Sounds sensible.
Hey, well, it's generally used for smaller areas. The source mentions typically less than half a square mile. Think like a single housing development, a shopping center parking lot.
Okay, small scale. And the formula. The sources called it fun.
Maybe for engineers. It's Q equals C times I times A.
Q equals COI.
Okay, break that down.
Q is your peak flow, the number you want, usually in cubic feet per second, or CSS.
Okay.
C is the runoff coefficient. It's meant to represent the surface type, like how much water runs off versus soaking in.
Dimensionless, right, just a ratio.
Well, mostly. We'll come back to that.
Okay.
Is the rainfall intensity how hard it's raining, usually inches per hour for a specific storm frequency?
Okay.
And A is the area of the watershed you're looking at, measured in acres.
Right. Now, you said mostly dimensionless for C, and the sources made a big deal about units here.
Yes. This is a really interesting bit, I think. If you look at the units, cubic feet per second for Q, inches per hour for I, acres for A, they don't naturally work out. Like inches per hour times acres doesn't equal cubic feet per second.
Not even close. And this is the key the source points out.
Yeah.
That runoff coefficient, C, isn't truly dimensionless in this formula. It actually has a hidden embedded unit conversion factor built into it.
Whoa, really? So the C value itself fixes the math.
Kinda, yeah. It makes the inches per hour and acres magically turn into cubic feet per second. It's a bit of, well, engineering magic, or maybe a mathematical shortcut that you just have to know is there.
That's fascinating. So it's not just about, is it pavement or grass? It's also doing unit work.
Exactly. And speaking of pavement versus grass, that C value itself, the sources highlight how much it can vary.
Oh, yeah. How much?
Well, it depends not just on the surface type, but which reference book or manual you pick up.
Seriously?
Yeah, the source gave examples just for forests. The PE reference manual might say C is 0.059 to 0.20.
Okay.
But a city manual, like Fayetteville, Arkansas, might list 0.15 to 0.30 for forests. And Washington State or Florida, maybe 0.10 to 0.30.
Wow, that's quite a range. For the same land cover type, 0.06 up to 0.3.
It's a huge spread. And that's just for forests. Obviously, urban surfaces like asphalt, concrete, roofs, they have much higher C values, closer to 1, because almost all the water runs off.
That variability, though, it definitely makes you think about the precision of the final Q calculation, doesn't it?
It certainly does. If your input C can vary by a factor of 2 or 3, depending on the source.
Yeah. Okay, so that's the rational method. Good for smaller areas, has that quirky C factor. What's the other method?
The other main one discussed is the NRCS rainfall runoff method.
NRCS, that's the Natural Resources Conservation Service.
That's one. Developed by them, formerly the Soil Conservation Service, SCS. This method isn't limited by size like the rational method. You can use it on pretty much any size watershed, as long as it's reasonably homogeneous.
Homogeneous meaning similar characteristics throughout.
Yeah, similar soil types, similar land cover.
And the formula looks a bit more involved.
It does. Q equals P minus A squared divided by P minus A plus S.
Okay. Q equals PA plus S. What are PA and S?
Right. So Q here is the runoff depth in inches over the watershed for a given storm. Not the peak flow rate like the rational method, but the total depth of runoff.
Okay. Inches of runoff.
P is the total precipitation depth for that storm, also in inches.
Makes sense.
A is the initial abstraction. That's the first bit of rain that doesn't run off. It gets caught on leaves, soaks into dry ground immediately, fills puddles, also in inches.
Initial loss.
Exactly. And S is the maximum potential basin retention. Basically, it's a measure of how much water the watershed could potentially hold or soak up if given enough time and rainfall, again in inches. So PA is like the effective rainfall that's actually available to become runoff.
Okay, so the runoff Q depends on how much rain is left after initial losses. PA relative to how much the watershed could potentially hold. S. How do you find S?
S is calculated from something called the curve number, or CN. The formula is S with thousand CN10.
Curve number. CN. Okay, what's that based on?
The CN is the really clever part of this method. It combines two key things. The surface cover type, like is it lawn, woods, pavement, roofs, and the hydrologic soil group underneath.
Soil group. Like sandy soil versus clay soil.
Exactly. Soils are grouped, usually A, B, C, D, based on their infiltration rate, how fast water soaks in. Group A is sandy, high infiltration. Group D is clay, very low infiltration.
Ah, I see. So the CN captures that interaction. Pavement on clay soil would have a really high CN, right? Lots of runoff.
Very high, yeah, close to 100. Whereas maybe a good pasture on sandy soil would have a much lower CN.
Less runoff.
Significantly less. So the curve number packages up the land use and the soil's ability to absorb water into one index number.
That makes sense. And the sources mention this method also has assumptions?
Oh, yes.
Yeah.
Like any model, it's built on certain assumptions about how rainfall and runoff happen. We don't need to list them, but it's important to know they exist, that it's not a perfect representation of reality.
Right. Good to keep in mind. So these two methods, rational and NRCS, they're the traditional tools for figuring out that peak flow or runoff volume.
That's right. They're widely used for designing that traditional infrastructure. The pipes, the channels, the detention ponds sometimes. They quantify the flow you need to manage.
And this ties back to LID because these methods essentially quantify the problem that LID is trying to address differently.
Precisely. The sources position these as the baseline calculations for conventional design. LID tools and approaches aim to reduce those calculated peak flows and runoff volumes right at the source, using more sustainable, nature-based practices.
Okay, so future discussions might compare, say, the Q from the rational method for a site versus what you might expect if you use LID techniques there.
Exactly. That comparison highlights the potential benefits of LID.
Okay, let's sort of wrap up this deep dive then. We looked at how low-impact development, LID, is really about managing runoff by rethinking the water cycle locally.
Yeah, distinguishing it from just building drainage pipes.
Right. And we explored those big downsides of the traditional diverted away approach.
Yeah.
The huge life cycle costs, the environmental damage from concentrating pollutants.
And potentially lowering local groundwater tables.
Then we defined peak runoff, that maximum flow rate during a storm,
The key number for sizing traditional infrastructure.
and dug into the two main calculation methods from the sources. The rational method, QCIA, for smaller spots with that really interesting hidden unit conversion in the C coefficient.
And the major variability challenge in picking a C value.
Definitely. And then the NRCS method, relating runoff depth to precipitation, initial losses, and the basin's potential storage.
All right. All driven by that curve number, CN, which cleverly combines the land cover and the soil type.
Understanding these calculations, even just the concepts behind them, gives you that critical context, doesn't it?
It really does. You see what engineers using conventional methods are trying to handle, which helps you appreciate why alternatives like LID, focusing on infiltration and on-site management, are gaining traction. It's a different philosophy.
Yeah, working with nature instead of just fighting the water away, it gives you a much deeper appreciation for how complex managing water really is. And thinking about those methods, particularly that variability in the runoff coefficient we talked about, where different official sources give you significantly different numbers for the same thing. And also knowing the NRCS method has its own set of underlying assumptions.
Right, they're models, not perfect reality.
What questions does that raise for you, the listener, about the certainty, the precision we actually have when designing billions of dollars worth of infrastructure based on these calculations?
That's a really important takeaway. How much certainty is baked in.
Yeah. Definitely something to mull over. What stood out most to you in this deep dive? Think about it. We'll catch you on the next one.